How does Helmholtz free energy connect to statistical mechanics? Have you ever wondered how the tiny particles in a system relate to the big picture of thermodynamics? Let's break it down, focusing on Helmholtz free energy and its ties to statistical mechanics. Helmholtz free energy is a key concept in thermodynamics, defined as the internal energy minus the product of absolute temperature and entropy. This equation tells us about the maximum useful work we can extract from a closed system at constant temperature and volume. When a system undergoes a spontaneous change at constant temperature and volume, the Helmholtz free energy either decreases or stays the same. It reaches its lowest point when the system is in equilibrium. Now, how does this connect to statistical mechanics? The answer lies in the partition function, which is a sum of all possible microstates of the system. Each microstate is weighted by the Boltzmann factor, which considers the energy of that state and the temperature. The relationship between Helmholtz free energy and the partition function is expressed in a simple formula. Helmholtz free energy equals negative Boltzmann constant multiplied by absolute temperature times the natural logarithm of the partition function. This formula links the microscopic behavior of particles to the macroscopic properties we observe. Statistical mechanics acts as a bridge, connecting the tiny world of particles to the larger thermodynamic quantities like Helmholtz free energy. By calculating the partition function, we can determine the Helmholtz free energy and predict how a system behaves at equilibrium and during spontaneous processes. This connection is especially important when we think about irreversibility and equilibrium. Since Helmholtz free energy decreases in spontaneous processes, it serves as a guide for understanding equilibrium under constant temperature and volume. Statistical mechanics explains this tendency by showing that systems favor states that minimize Helmholtz free energy, balancing internal energy and entropy. In practical terms, this connection helps us model various phenomena, including chemical reactions and phase transitions. For example, in physics and chemistry, understanding Helmholtz free energy allows us to predict how systems respond to temperature changes and how much work can be done without altering the volume. So, the next time you think about how particles interact in a system, remember that Helmholtz free energy and statistical mechanics work together to give us a clearer picture of equilibrium and spontaneity in thermodynamics.